If you haven't watched the previous embedded video, you really should do that first. This was made assuming that you had viewed that introduction to the idea, so I'm going to take some shortcuts here and there that might not make sense without that background. As we work on writing these two net ionic equation examples included here, we need to keep these three questions that were posed in the last video in mind. I'm not going to use the animations in this video that I did in the last, as you won't have access to similar tools come quiz time. But we're going to think about things in that same way. Our presentation of the idea is the only real change. I'm going to walk through this first example with all of the steps to illustrate why we do what we do. Then I'll do the second example with fewer steps. Here we're given the formula unit equation. This type of equation lets the chemist know what to look for on the shelf in the stockroom in order to prepare their reagents. It also lets them know what to expect in terms of products, but it does little to show what is actually happening in the reaction mixture. If you haven't really written net ionic equations before, a good first step is to rewrite your equations in terms of the ions that would be in the beakers. We call this the total ionic equation. And this is the equation we want to review if we need to know exactly what is happening in the reaction mixture. If a formula unit is aqueous, then you will write the products for the dissociated salt, just like you did in an earlier example in this page. If the formula unit is a solid, then you will leave that solid together, just like the lead 2 iodide that was in the bottom of the beaker in the precipitation reaction video. These total ionic equations get lengthy, but this step allows you to see what you have floating in solution and what has formed a precipitate. It also lets you see if there are any variables that are unchanged from one side of your equation to the other side of your equation. There are two aqueous sodium cations on the reactant side and two aqueous sodium cations on the product side. Similar story for the two aqueous chloride ions on each side of the reaction arrow. Much like the variable x would cancel across the equal sign in an algebraic equation, these variables will cancel across the reaction arrow. If you think back to the image of the final beaker in the last video, what we just crossed out are those dots that were still floating around unchanged in the final larger beaker. They're the ions that watched everything else do the work, or in other words, they're our spectator ions. Since they're unchanged, they aren't part of our story. What is part of our story, though, is everything that is left in the reaction. This includes the sulfate anion and the barium cation that come together on the reactant side to form the insoluble salt on the product side. This, my friends, is our net ionic equation. It tells us only the important details of the chemistry occurring in the reaction, only shows us the ions that come together to form the precipitate, only shows the net of the equation without the fluff of the spectator ions. This is what we were aiming to write, and we are now finished with our problem. A proper net ionic equation will be both atom and charge balanced across that reaction arrow. It will also include states of matter. For our class, we'll have two aqueous ions that come together to form a single solid product. Could I have done that last one a bit more quickly? Absolutely. Watch this, but keep in mind that this approach only works because all of that extra work we did with the other method. Start by reviewing your products, specifically their states of matter. Barium sulfate is a solid, and sodium chloride is aqueous. Anything that goes into the aqueous compound on the product side had to be aqueous on the reactant side as well, at least for our purposes. Which means that ions that make up the aqueous product have to be spectator ions, which also means that they would not show up in our net ionic equation. You translate that to ignore the ions that make up the aqueous product when writing net ionic equations because they are spectator ions. That leads us to focus on the solid product. There is a barium cation and a sulfate anion that make up that solid product. Now, the downside of this method is that you have to remember to include the charges on the ions when you write the final net ionic equation. It's easy to forget them, and many students do. Since ions come together to form the product, ions, and not neutral species, they have to be included on the reactant side of the equation. And if correct charges aren't included, your answer is considered incorrect. All right, let's try one last one. Reviewing the products, we have aqueous potassium nitrate and aqueous calcium hydroxide. Remember that most hydroxide compounds are actually insoluble, but calcium is listed as a partially soluble exception. All of the ions involved with that potassium nitrate are not really relevant to the chemical process and will just be spectator ions. They will not show up in the net ionic equation. Because we listed the calcium hydroxide as aqueous, the same story is also true there. The calcium and hydroxide ions are also spectator ions. That means that there isn't an important product here. You didn't make a solid. You started with ions in solution and you ended with ions in solution. So here, the answer to the net ionic equation is no reaction because no reaction has occurred.